Hi, Kisei.
Hey, good morning. Can you hear me?
Yep, I can.
Oh, okay, nice.
So just like last time, I'll welcome everybody. I'll introduce myself, and then you can introduce yourself.
Yeah,
And then I'll do the next slide and just again remind people that they can see our previous seminars here. Um, and then I'll go to this slide
after
and you
the
can, oh,
yeah, and maybe I can talk about Faith's short bibliography,
yep,
like right, yeah, like
yep.
he graduated
After,
from blah blah blah. Yeah,
yeah, after this one,
after
I'll
this
pass it to
slide, yeah,
you
yeah,
and
yeah,
then you can do this
yeah,
whole thing and then we'll let him share.
yeah.
Okay. I'm kind of surprised the microscope came already. I don't know why I thought it would take another month or so.
Actually, the sales representative said something like 3 weeks or 4 weeks.
Hmm,
Yeah. So
okay.
yeah, it looks like it's time. Yeah. I was very surprised that the milling machine was delivered actually 3 weeks ago.
Me too. I mean, I
Yeah,
was surprised it was delivered so quickly and that it was kind of lost, but
yeah,
I don't know. Hans
yeah.
is
So
probably like, oh
actually,
my
the
God, what's
this
happening over
yeah,
there?
and actually this milling machine weight was actually 250 pounds.
Wow.
Yeah. So now we need to think about which kind of table we should prepare to leave
Mm,
it. Yeah.
yeah. I was still thinking that it would be best to put it in the mezzanine where it's hidden away. I don't know. What do you think?
I think so. Mezzanine area
Yeah.
is best place to, yeah. Yeah, I think so. Yeah.
I'm trying to think if
And yeah,
any of the equipment in the other lab is that heavy, but I don't think so.
I think we already come up with all of the idea about the equipment, I guess. So now I a little bit, I quite think about the platinum and gold crucible for the gas mixing furnace. Yeah,
Yeah, I
I
did
think that
go ahead.
in a Christie's lab also has this kind of stuff.
Yeah, I don't I will look and see if I can find an invoice for that. I don't know if we'll have that on the drive, but I did text Jill at Carnegie, Faye's lab manager, to see if she remembered who we ordered
Mhm,
from the last time because I think Faye and my postdoc advisor put in like a
mhm.
joint order.
Yeah, I think the supplier Heras or something I cannot
Mm,
pronounce. That's the sort of the monopoly around us, I
mm,
guess. This is
okay.
German company. Yeah, yeah. Kurt also said something about the same idea. So
Yeah.
yeah.
I thought we had just bought them the last time from like, a scientific supply company, but because I remember like the way it was packaged and its little card, and I feel like I remembered the name of the company, like it was familiar to me, but the other one, the one that begins with H and then none of us can pronounce, I don't remember seeing that one before, but
Hmm.
we'll find out.
Yeah. I'm also curious how Carnegie get the yeah, or even if yeah, failure coming here.
Yeah, maybe I should double check that you didn't email or anything. Doesn't look like it.
Hello, Dr. Mueller. Thank you for coming from Germany. Yeah.
Okay, I emailed him, so we'll see.
Oh, okay. Kara, do you know this mascot?
Yeah, from Bucky's.
Yeah. Yeah. Bucky's is basically only in Texas and maybe few other states, maybe
Hmm.
I forgot Oklahoma or Alabama or somewhere. But yeah, I I remember that the gas station Bucky is very clean. Everything is
Oh,
very clean and
okay.
yeah,
Good to know.
yeah, yeah. All over the Texans like Bucky's, yeah, rather than other gas station along the freeway.
Yeah, QT is really big here, but I actually can't remember if I've ever used the restroom. So
Mm.
I don't know.
And there are they sell also sell good beef jerky and
Mhm.
yeah,
Yeah.
and some kind of shredded pork burger sandwich. Yeah,
Oh, okay.
something. Yeah, and with some good barbecue sauce or sort of the Texas style
Nice.
taste. Yeah.
I had a really good, when I was in Houston last, I had a really good burrito from a gas station. It's like by near NASA. I
Oh.
forget what it's called, but it's like a space themed gas station inside. You might know
Mhm.
the one. Um, really
I
good.
guess I can know. Yeah.
Yeah. Okay. No answer yet.
Oh, okay.
Hi, Faye.
Hi.
How are you?
Good, good, good.
Yeah. Nice to meet you, Faith.
Hi.
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 Uh,
Here, so.
Do you want to test sharing your slides so we can make sure everything's okay?
I hope so. So let's see, share screen. You seeing my full
Yep.
screen?
Yep, looks good.
Okay, good.
And yep, I can see your cursor too, so looks good.
Okay, all right. I guess I can just leave this as
I have a couple of slides to
oh,
show before you start your talk,
okay,
so I'll give the share
okay.
back to you once I'm done with those.
Yeah, okay, let me stop share. How things in the SU, where things are. You guys
Things are pretty good. The lab construction has started. It's really exciting. We got pictures of like acid resistant waste lines and stuff like that. So there's big holes cut in the walls so we can move in the presses. And the 6,000-ton press will be installed starting in September. So it's already finished. It's already packed up, like disassembled and crated. I think it might already be on a ship. It's supposed to be
Yeah,
supposed
it's
to be shipped
almost time. Yeah.
mid-month.
yeah.
Yeah. Yeah, it's
So
really
who
exciting.
is building the big press? Who is
Sumitomo.
building the big press?
Sumitomo.
Oh, Sumitomo.
And QC got to go
Mm.
there and see it completed and after they did the final testing.
Yeah.
So it's similar to the Ihime
Y-
press.
Yeah, almost same design, yes, as Ehime's Bochan press. Yeah.
Okay, okay,
I think the main
good, good.
difference is that the cradle to turn the guide block, right?
Yeah, yeah. That's the basically only the difference. Yeah.
Hi everyone, we'll get started in about 3 minutes past the hour. How are things at Carnegie? Have you been away at lots of bean lines recently?
No, the APS is done. So, well, yeah, in the spring before shutdown, we had lots of bean times, and but now a little bit slow, and hopefully we'll get some times in Europe. So in the summer, in the fall, maybe travel to Europe a little bit.
Oh, nice.
Okay. Faye, are you going to EMPG?
No, but I am going to Edinburgh for the Europe meeting.
Oh yeah, cool.
Yeah, there were just too many meetings, and I had
Yeah.
to skip a Goldschmidt too.
Yeah. Okay, everyone, we'll start in just a couple minutes. Okay, hi everyone. Welcome to the last FORCE seminar of the semester. Thank you all for joining us here today. I'm Kara Brugman. I'm a research scientist and the outreach coordinator for FORCE.
And I'm QC Tsuno, research scientist at both at ASU. Yeah.
And before we begin with Faye's talk, I just want to remind everybody that this meeting is being recorded and will be available on YouTube next week. If you have a colleague who missed it, they can go and see it when it's posted next week. You can also see our previous seminars with Sally June Tracy and Bin Chen, which are posted there right now. And please do sign up for our mailing list at force.asu.edu/newsletter to get updates on our events and future seminars. We'll be starting up again in the fall with 3 more seminars. And we're also on Twitter, LinkedIn, and Instagram. Okay, without further ado, I'll pass it over to Kisei.
Yeah. And yeah, let me introduce today's speaker, Dr. Yingwei. So he works at the Carnegie Institution for Science for decades after graduating City University of New York for obtaining the PhD. And he's familiar with March-Anvil technique, shockwave experiments, diamond anvil apparatus to understand the comprehensive geologic processes. And recently, iron titanium oxide mineral discovered in shocked Martian meteorite was named after Faye. That's a very good one. Yeah. Then, yeah, it's time is all for you, Faye. And yeah, and thank you for giving us the presentation.
Okay, great. Let me share my screen.
And everybody, if you want to ask a question, you can raise your hand after the seminar is concluded, or you can also type your question in the chat and I'll ask it for you.
Okay. Well, thank you for the invitations, and it's a great pleasure to present some of my recent research. And unfortunately, we can't see, it's not in-person presentation, but I see lots of familiar names on the screens. So, and thank you for joining us. And hopefully, when the force and the press is finally arrived, that we will all be happy to come on site and visit and see the actual press. But for now, it's it's a good to keep this communications before the lab is fully functional. So I'm going to talk a little bit broadly and about the high pressure, and I had a little bit difficult to come up with more target titles, so I end up with a very broad topic, which means I can talk about whatever I'm interested to talk about. I hope you will find interest. And let's see, how do I advance? There's high pressure developments over the years, and there's various different techniques, and but my interest mostly on planetary interior, include those terrestrial planet and Earth, and recently super Earth, and so they all requires higher pressure, high temperature simulation to reach the center of the planet. And for Mercury and Mars, you need 36 GPa, which is kind of reachable pressure range with a larger volume apparatus. And if you want to reach in the center of the Earth core, and currently you can do laser heat in the diamond anvil cell, be able to simulate this pressure and temperatures, and with some challenging to get above 300 GPa, but hopefully become more routines. And if you're really interested, super Earths, and they can easily get to pressure in the interior and larger than terapascals, and so there you need dynamic compressions and be able to reach those pressure. And static compressions also have been trying to approaching those pressure, but mostly at a room temperature right now. And on the other side is material synthesis, and always want to go into a high pressure, but more importantly, get to larger volume for a certain pressure range. And so one of this talk, I'm trying to emphasize some of the development we have been doing, and trying to focus on optimize the volume for a certain pressure range, and be able to do synthesis for various novel materials. And this is also in line with the development of the force, and really want to go into larger volume, and but ultimately with a larger volume, pressure will be limited. And as you can see from this presentation, I will hope give you a balanced view on what approach we should take in terms of optimized volume versus ultra high pressure. So this is a kind of outline what the pressure temperature space, and I have personally been interested, and I've been working on piston cylinder multi-anvil in a low pressure end with larger volumes, and then for most of the Earth core mantle physical property measurement, particularly with synchrotrons using diamond anvil cells. And I have been collaborating with people and doing traditional gas gun experiment. More recently, we have been conduct experiment using the Z machines at the Sandia National Lab, and achieve over terapascal pressure range, and mostly for understand the interior structure of the super Earth. So I am going to very broadly kind of speaking and give a pretty brief overview of the high pressure techniques for the benefit of some students online. As far as I understand, there's also students participating in this seminar series. And so very briefly talk about static compression method and the dynamic compression method. Then I want to transition to talk about velocity measurement and the dynamic compressions. And the there's two projects, and which is really kind of fit nicely for this synthesis and the themes in terms of making a larger samples. And you will see from the presentation is intimately related to the success of the large volume synthesis. And then in the end, I want to briefly talk about some of the latest development using polycrystalline diamonds as an envelope for multi-envelope experiment. And we also have some success in using a toroid diamond envelopes and to reach a multi-magma pressure in diamond envelope cells. So that's pretty much what I will be talking about. And so start with large volume synthesis, and this is really kind of driven in the early 50s, and there's a race and to make a synthetic diamonds, and many groups have developing a large volume apparatus trying to be the first one make synthetic diamonds. And nowadays, majority of diamond is made in using a cubic hydraulic press and those 6 pushing envelopes, and there's some still using a belt apparatus. And the imaging here, gigantic belt apparatus, and you can make a very large quantity of the synthetic diamond. For the cubic press is the same. And basically, you can making several inch cubic diamonds, and there's also on the market you see lots of synthetic single crystal diamonds in the jewelry market. But one of the significant development in earth science is this press showing under here as a Boyd Ingram press, and that's a press I inherited and still in my lab is operational. It's a piston cylinder apparatus and developed in the early 50s, and really kind of utilized to simulate the pressure temperature condition down to 100, 150 kilometer depths, and really revolutionized our understanding of the low crust upper mantle petroglyphs. And in the 80s, and there's quite a bit of, in the early days in Japan, and has developed the multi-envelope apparatus, but was less known in the United States. And when I was a graduate student, and people started interested to bring the multi-envelope into United States, and I was at the time, and graduate students, and seeing the first multi-envelope imported from Japan to Stony Brook was Bob Lieberman, Don Widener is leading, and we were also the group of the Center for High Pressure Research that predates to the compress. I mean, it was young people probably don't know. But that's where it started as a multi-envelope development in the United States. And nowadays, and there's many multi-envelope lab, and particularly was the development of the walk type of modules, and it become very popular. And all you need is have a larger tonnage hydraulic press, and then you can have various insert, and the bulk of the high pressure experiment in the United States and in the world is really done with 1,000 tons or 1,500 tons press. And because for that type of tonnage, you basically can achieve the full pressure range can achievable with the tungsten carbide up to probably 27 GPa range. So this is really a significant advance in the last several decades in terms of high pressure research with a larger volume. And of course, recently there's several groups and interested to developing and already developed much larger tonnage press, and like the one I showing here imaging, and also Bayreuth, BGI has 5,000 ton press. I know several labs in China has larger ton-rich press has developed now, and the SU will be leading the United States effort into developing a larger volume apparatus. And those are certainly very positive development and advantage. You will be able to make much larger samples, and if you're interested to synthesize the larger samples, such as like polycrystalline nano transparent polycrystalline diamonds, and those you can make to the centimeter size and with this type of apparatus. So this is really a very exciting times, and with SU and the new lab to be established in the near future. But what I want to talk about is actually some of the development my lab has been doing, and mostly two directions. One is trying to optimize sample volume at a certain pressure range, and also trying to extend it to a higher pressure, and mainly to utilize sintered diamond envelopes and for multi-envelope experiment. Sintered diamond envelope has been around for a while, particularly and developed by Ito and at Misasa, and there are several Japanese groups recently have also been pushing the limit with the sintered diamond. Most of the sintered diamond envelope using relatively small cubes, and typically we use a 1-inch cube or 32 millimeter tungsten carbide cubes, and as far as I know, no one has extensively using 1-inch cubes. So we are actually pushing to using 1-inch cubes and optimize the sample volume. So this will play a role in some of the projects that I've been doing in the last several years. But we also have been trying to pushing higher pressure, and there's a group is doing much higher pressure, to even 100 GPa, but mostly at room temperature. But I'll say to 50 or 60 GPa, people have been successfully achieve those pressure range. But in general, those are very costly experiments. So what my goal is trying to find a compromise in certain pressure range and can be routinely done without much of the cost aspect. So that's my effort of the extended to high pressure, and so not to the expression a pressure to a 50 or 60 GPa. I'll be happy and get to a 35 GPa. But this is also related to my scientific goal. I just want to be able to reaching for those experiments, reaching the center of the Mercury or Mars. And so I have other techniques that can go to much higher pressure. So it's not really my goal to pushing the limit of the in the multi-envelope with the sintered diamond. And whenever you're trying to push in the limit, it's always going to be costly. So I'm happy to see other people doing that too. And so the other aspect, technique I use is diamond emerald cell. And over the years, we have done lots of equation state, the physical property measurements, and particularly with synchrotron X-ray diffractions. And we have done some Raman and infrared spectroscopic and very popular techniques. And using this symmetric cell is very portable and being taken to the synchrotron, doing very easily doing diffraction work. And over the years, I'm also interested the various heating techniques include external heat, like here, and then internal resistant heat. We did a couple of papers on the phase diagram of iron and also laser heating, and particularly all those laser heating has become available at the synchrotron facilities. And so with a diamond anvil cell is certain can pushing multi-megabar pressures, but more routinely than up to 150 GPAs, and with coupling with the laser heating, you can easily simulate the core mantle boundary conditions. And but if you want to reach in the core pressure range, and that will be requires more effort. And but this all comes at the cost to go to higher pressures. Obviously, the sample will drastically decrease, and was a piston cylinder going to centimeter size of samples down to millimeter in the multi-anvil. When you go to core pressure and above, 200, 150 GPA, you are down to the sample size and order of 20 micron diameter, very thin, 5 micron thin samples. So those are really as a trade-off and higher pressure and sample volumes. It really depends on what question you're asking, what your scientific goal. And for physical property measurements, and many of the like density measurement, you certainly can, using diamond anvil cell get not requires much of samples, and to be able to get high quality data. And of course, if you're interested in material synthesis, and then you always want to get some quantity of samples, but it is a complementary. You can use in diamond studies, a diamond cell study, and to try to understand the properties, the effect of the pressure, then trying to design the pathways and be able to reduce the pressure, make the same materials, and those are really very useful complementary method, and particularly if you are involved in high pressure research. And I always benefit from be able to using different techniques and look at the different aspects of the problem. So of course, there's dynamic compressions, and with the gas gun, laser shock, and the pulse-powered shock, and you can access simultaneous high pressure and high temperature around the Hugonia. Now with ramping compressions, you can also keep at a lower temperature, goes to higher pressure and stay in the solid. And I believe my colleague Trace and Sally Trace has given a talk on this similar series, and she has probably talked extensively on the dynamic compression method. But I just want to, for compressions and kind of mentions, and there's a static compression method and the dynamic compression method. So this is a very brief kind of introductions to the high pressure techniques, and particularly for the students, as well as some of the people outside of the high pressure research. And but what I want to transition to is talk about one of our pandemic publications, and now is not so new, but still relevant. And that's a paper we published 2021. And it's really a very good demonstrations how the static dynamic method can be combined, and to utilize the synthesis of using a multi-anvil apparatus and doing unique dynamic compression experiment. So this paper was published, and mainly on the melting and density of MgSr3 bridgemanite, and the key aspect of this experiment is start with the synthesis of the bridgman examples. So we know bridgman unstable above and certain pressure, and typically above around 25 GPa, and for the Earth, and that's a dominant low mantle minerals. And but making a substantially larger sample is still relatively challenging, and we want to do some dynamic compression, start with a denser silicate rather than its low pressure form as insertite, and the advantage is almost 30% of denser than the low pressure phase, and we can substantially alter the Hugonia path and access different PT paths. So that was the motivations to really start doing using bridgmanite as star material. Of course, for the density measurement, we can avoid all the phase transformation, directly get a density and pressure measurement and for the high pressure phase. So as I said, really as the advantage is to access different Hugonia paths, and this is showing a temperature and the pressure diagrams and for a silicate melting curve. So typically there are quite a few experiments done with for using insertite as a star material shock to a high around the Hugonia. So basically temperature rises up very fast and pretty much crosses the meltings below 200 GPAs. So with a dynamic compression, there is some constraint on the melting of MgSO3, and using insertite as star materials around 180 GPA, there's the melting determinations. And what we want is be able to look at as a crossover with the melting at a much higher pressure. And so this can be done with a denser bridgmanite, and so the Hugonia will goes to substantially higher pressure crossover with the meltings, and in this case, and could be as you will see, will be around the 500 GPA. So that give us really a good constraint on the melting point at a much higher pressure. So the first challenging is to make a substantially larger star materials for dynamic compressions, and we have initially tried with tungsten carbide, and we did occasionally make bridgmanite and relatively large bridgmanite, but it was still costly because the success rate was very low, and even sometimes the synthesize, you break all the envelopes, and until we start using sintered diamond cubes, and those are not just small sintered diamond cube, but we're using a 1-inch size of sintered diamond cubes, and with those we can consistently making bridgmanite larger than 2 millimeter size, and because for those dynamic compression, each experiment we need about 4 to 6 samples for each shots, and for the total project that we were envisioning is like 40 samples, and that's substantial synthesis and required at those extreme conditions. And as is showing here, a scale 1-inch cube is substantially larger than typically people using a 14 millimeter sintered diamond cubes, and especially if you go into a larger truncation, that's later. More recently, we're using a larger truncation too. But for those syntheses, we're still using a 3 millimeter truncations and be able to consistently make a bridgmanite. So those experiment can be done at the Z facility at Sandia National Lab, and basically we are making many and bridging discs and on the order of 2.5 millimeter diameter and ranging from 0.3 to 0.9 millimeter thickness, and they're mounted to a target and take only a couple of milliseconds to destroy everything. So, but of course, in this process, we do get data and from the visors where we be able to process, get the density and the sound velocity data. So this is only can be done with the teams, and we have experimentalists and modeler and also theoreticians and doing the calculations and the whole team. It's a teamwork and make this happen. And for typical Z shots, and this is showing one of the target, and basically we have 3 bridgman example. There's also diamond, transparent diamond sample will mount to the next 2 years because as the project was also coupled, there was another project doing the diamond shock. So with the 3 examples, the different thickness, we actually be able to get some sound velocity data. This is turned out to be a very critical to determine the melting temperature. So with different thickness of samples, and we eventually be able to get a catch-up thickness, and from there we can derive the longitude sound velocities. So this is showing the velocity versus the pressure. And what you're seeing here is this red square is measured velocities, and the red one is, those are definitely solid VP measurements, and they're consistent with the VP of the bridgmanite calculated VP and bridgmanite, and down here is the box sound velocities, and there is measurement of box sound velocity from the laser shock, as well as I think maybe some gas guns was insertite as a star material. As I said previously, if you use the insertite that goes to melting at the relatively low pressure above 200 GPa, you will see liquid liquid MgSO3. So those are become box sound velocities, and we're seeing a clear drop from the sound velocity measurements and up to 1,900 GPa, and we are seeing a drop at 500 GPa, and it's clearly showing onset of the meltings. So with this information, although this is, you can see the uncertainty is larger, but it's sufficient to identify is a solid velocity or liquid velocities. So with this information, if we plot the temperature and pressure diagrams along the calculated Hugonia, you will see we clearly have 2 shots in the completely solid and based on the sound velocity as well as the waveforms, and 3 experiments in completely in the liquid and along the liquid Hugonias. And this interesting shots is at a 500 GPa, which is showing some drop of the VPs, and we estimate the cross-sound ratios, estimate the possible temperature between the solid Hugonia and the liquid Hugonias. And that gives us a constraint on the melting curve. And if you extrapolate back was the laser heating the data and the cross, and there's 2 data shockwave data. So one is from the gas guns and using insertite as a star material, showing substantially higher melting, and there's a laser shock is showing, and also use the insertite showing lower meltings. And we are interpreting those data probably in between, because we clearly see our shots at a 420 GPa is a solid, so the melting curve has to be above the solid shots, and so this is our proposed melting curve. And if you're interested in details, certainly you can find on the Nature Communication paper. And of course, we also get high quality density measurements, because each of those shots, we have at least 2 samples in the repeating and density measurements at the same conditions. And so those are relatively high quality density measurements. And we, if you put this calculated temperature on those around the Hugonia, and basically we can get some ideas on the thermal equation state by combining the static room temperature compression data. So that's where we derive the thermal equation state using the combination of these 2 data sets. And with this data, we can actually modeling very simple model of the super Earth and the density, interior density profile by assume a pure iron core and in the member MgSr3 and mantles. And this is showing 2 typical density profile was assumed temperature profiles. And this is important for super Earth and exoplanet study. And there's many observations on the super Earth, and with a relatively larger uncertainty in terms of the ratio and mass. But for mineral physics point of view, we need to provide a fundamental framework in terms of end member density profile. So this is showing iron based on previously laser shock from Livermore groups and our new MgSr3 and end member. So the idea is we provide some kind of reference mantle or core density profile with the end member. Then from there on, you can infer either the ratio of the mantle and the core, or composition variations, how compositionally going to affect the densities. And that's pretty much the same concept we use for core density deficit is based on pure end member. So we want to, advocate for end member MgSr bridgeminite density profile and looking at the mantle density excess, because most of the density profile is going to be denser than this end member density profile. Like in the core density deficit is a concept. Most of the light element is going to lower this planetary core density compared to the pure iron. So I think it's a very useful concept, and look at the chemical variations. And although we're still far from some of those constraints we would like to see in terms of density and velocity measurement, density and radius measurement of the exoplanet. So I want to transition to another topic we have discussed and published on the shear velocity of the inner core. And this is another project that really tied to this synthesis of the larger samples, and those experiments done on the traditional gas guns. So we need a target and on the order of centimeters. So those are 12 millimeter samples. So we looked at as iron silicon alloys, and those disc is centered at a 5 GPa with a cubic envelope apparatus. Not particularly this apparatus, is actually a more traditional cubic envelope apparatus and used for diamond synthesis in China. So the idea is to look at the shear velocities of the solid inner core, because the shear velocity is substantially low, and traditionally we are thinking this observe the low shear velocity in the inner core is probably due to either compositional effect or temperature effect. So what we designed the experiment to look at if a silicon alloy can lowering the shear velocity as well as temperature effect. So this can be done with shock experiments around the Hugonias, with star material was synthesized the cubic envelope apparatus. And the paper is very recently published, and in 2022, and about a year ago. And we have looked at the effect of the silicon on the sound velocities, and mainly trying to understand the temperature effect as a silicon effect, whether it will low substantially shear velocity. And the conclusion came out is none of them can explain the low shear velocity. So we need to find another solutions. But I want to just use in these examples and how we can utilize larger larger volume synthesis and to doing dynamic help in doing some of the unique dynamic compression experiment. So in order to get a shear velocity is really difficult to measure, and particularly at high temperature. And but shear velocity is related to the compressional and Bach sound velocities. And if you know the P wave and Bach sound velocity, obviously you can calculate the shear velocities. One of the techniques you can use in the dynamic compression is the reversal impact techniques, and that's why those syntheses become important. So basically, we're using the sample as a fly and doing a reversal impact and get this P wave and Bach sound velocity at the same times. So those are basically done with the traditional gas guns, and we can get Bach get the longitudinal Bach sound velocities, and then looking at this elastic plastic transitions and get this Bach sound velocities. So well, this is just showing one example of the 9% of silicons alloys, and we measured the VP and the Bach sound velocities simultaneously, and then derived as shear velocity, and those around the Hugonia obviously is a higher temperature. We compare with some room temperature measurement with the diamond cells, and they derive some of the temperature effect. And sound velocity measurement typically has much larger uncertainties than the density measurements, where on the order of, there's some uncertainties in terms of the measurement and in velocities, but still, and this is the first time we'll be able to measure in the shear velocity at those pressure and the temperatures with these alloys. So the story is we end up obviously if you add the silicon, you can match the density and of the inner core, but we will not be able to match with the same amount of the silicons. So we'll not be able to measure the compressional and shear velocities, and that obviously we could not explain observe the low shear velocity in the core with the silicon as a light element. So I'm going to use the last 10 minutes or so to just talk about some of the latest recent development, in particular in my labs. And as I kind of showed and what we really have been trying to optimize sample volumes and be able to make a substantially larger high pressure phase and for dynamic compression. This is really opens up lots of possibility for one is Altlin's Hugonia PT pass, and the two, we can literally access different and star materials. It's almost like a pre-compression experiment. So if you can using a dense silicate. So the example I showed is, the bridgmanite, obviously, there's people probably right now is working on linguadite and wurtzellite, archimodolite. I mean, we also have worked on the stishovite, have a set of data, haven't really processed yet. And those are become very important star material and for dynamic compression, particularly for laser shock, and requires much smaller samples. And those have become more feasible to using those dense silicate and high pressure phase as the star materials for dynamic compressions. I think will open up a new area, particularly with force type of larger press, and then we'll have a new way of doing dynamic compression experiment. And of course, for the larger volume synthesis for the material science is always important to get larger sample and be able to do all different kind of characterization as well as possible applications and the practical applications. And one of the recent, actually before I showing some examples, so I want to talk in general, on how you optimize sample volume, obviously, and for multi-envelope experiment, the sample volume is related to the truncation size, and but ultimately is tied to how much force is available to generate the pressures. And traditionally for the multi-envelope, we have a 1-inch cubes, and in my labs, we have 1-inch cube and 32mm inch cubes. And for larger press like a Hemis Bocho, and they're also using a 52mm cubes. And so those are tungsten carbide based and cubes. And so obviously for certain pressure range, and you can using tungsten carbide. But again, once you go to a 52mm cubes, the cost goes substantially compared to the 1-inch cubes. So those are the facts that we have to consider in terms of how to sustain and experiment can be done in a reasonable cost. And the key is to develop a stable assembly in a certain pressure range. So as I said, if you want to push the limit, you're always going to break the cubes. So you have to figure out your budget into that and to what type of experiment do. But another alternative way to doing this is like what I have demonstrated using a larger sintered diamond envelopes and going to, and now it's possible to make a 1-inch sintered diamond cubes, and as an envelope, although the upfront investment is larger, but if you can continuously use those at and the limit of the tungsten carbide, and then you still come ahead in terms of cost effective and in the long run. And again, it depends on what type of project you're pursuing. If you're using a sintered diamond, you only want to run experiment below 20 GPa, I can guarantee you, you'll never break the envelopes. Of course, whenever you have a brew out, I can't guarantee that. But if you have a stable And that's the way, the alternative way to get larger samples. So this is one of the development we have been one of the development in my labs is basically we're using 1-inch sintered diamonds, and right now I'm working on 8 millimeter truncation. So it's a traditional 14/8 assemblies, and we can generate pressure up to a 25 GPa at room temperature. Well, this is actually I using a step heating. So actually, when during the heat is you gain pressure. So here is showing the high temperature during the heating, and with step heating, we can get to a very high temperature, and we actually getting pressure around 30 or 32 GPa at 2,000 and 3,000 degrees, and those calibrate at APS GC cost. So that's one of the directions that basically uses the diamonds and trying to using optimize the volume. There's another aspect is if you don't want to optimize the volume but want to push in the temperature limit, and there's also some advantage because with a smaller heater, and particularly in this case we're using a step heat, you can go very high temperature and very little pressure loss, and partly because you have larger thermal insulations be able to push in a high temperature. So there's two aspects. One is optimize the volume. Two is to push in the temperature limit, especially if you're interested liquid melting. Right now I'm doing a deep magma ocean project, and basically we are looking at liquid silicate and liquid metal melting partitions. And of course, for using optimize the volume has advantage for making a larger sample. And this is a paper with my colleagues and in Jilin universities, and we made a larger sp3 carbon, and but not diamond. It's amorphous. It's a glass. So those this material has been synthesized in the diamond cell with a very small quantity, but with a larger volume, we'll be able to make a larger sample, be able to do detail the TEM and other property measurements, bulk sample property measurements, with a larger sample synthesis. And I have also working on mesoporous materials, and one of the goals we're trying to make mesoporous diamonds and mesoporous CBN. So that's something we also have to using larger volume synthesis and ultimately be able to make those material potentially could be used as a molecular filters, and with a tunable porosity and the size and distributions. And we also, I just give a couple of examples of the applications where this, and this is recently we published a look at this percolation and the deformations. And although this is not the downward sintered diamond, but potentially this is another applications. And those experiments were done with a hard aluminum, densified aluminum rod. And but we could easily replace those with the sintered diamonds and generate much more of the deformations. For example, and here you see rotation markers, and so potentially with the sintered diamond and techniques, you can also enhance those deformation experiments.
Hello.
And so so finally, I want to end the talk and was one of the very recent developments is someone is asked the question?
I think he was on the phone, a phone call.
Okay. So I want to just briefly mention some of I didn't talk about much of the diamond cell work, but this is very exciting, and the work Claire and Sarkowski worked with me on the toroid envelopes, and we are using FIP technology and to shape the envelope and pushing pressure to multi-magma pressures, and I believe we can now pretty routinely go above 300 GPa with this kind of diamond envelope cell compressions, and this is very important for Earth cores, and if we want to measure density, and we need a much better understanding of the pressure determinations as well as density measurement for different pressure scales, and density measurement of iron alloys, and up to the center of the core at a 365 GPa, and basically there have been this kind of development. I think 2018 there's 2 papers published on the toroidal cells and pushing pressure above 400 GPa, but most of those experiments done with very tiny tips, and I believe it's below 10 micron tips, and so most of those will be doing room temperature measurements. And but what we were interested is in the thing of the maximized volume. So we are trying to make the qubit as large as possible to achieve those pressures. So we have an envelope on the order of 50 microns, and we'll be able to push above 400 GPa with those designs. And this is primarily led by Zarkowski, and she's now at Livermore. And I just want to end really to talk about, I mainly talked about the optimized sample volumes and with a larger volume press, and those opens up a new possibility doing dynamic compression experiments, and is great potential for using larger sintered diamond envelope, not only for optimize the sample volume and also pushing some pressure range, not to the extreme pressure, but some pressure range, but as well as to pushing to the higher temperature regimes. And I think the key aspect is, besides have a larger press, and we need to look into super hard envelope materials, and that and as well as special envelope design. And as we demonstrate, if you're using the same single crystal diamonds, and you can generate pressure, from 100 GPa to 400 GPa just by different envelope designs. And the same applies for larger volume apparatus like the BGI biroid groups, as use the taped envelope to be able to push into 60 GPa in the using tungsten carbide. But again, those are costly experiments, and so we also need a balance between the cost and what is comfortable operational pressure range, and those are the elements or factor we have to consider in moving into a new design for a larger press and leading by the edge. So hopefully we'll keep the communications out and have thinking about what we can do with a larger press, but meantime also should put the effort to design new designs and new configuration and the new envelope materials. But ultimately, I want to say is really find the right techniques for your project. Every project, well, depends on how you design and find the right techniques is a key to successfully carry out your project. Thank you for your attention.
Thank you so much, Faye. It was a great talk. Do we have any questions from the audience? And of course, feel free to type them in the chat too. I see some clapping hands.
Maybe can I ask you one question? I'm curious to know from Arizona State. You said something like shear wave velocity of iron silicide alloy didn't match the sound velocity of the PREM model, right? So
Correct.
So you think that there's, of course, the RC's core has like another like candidate light elements like sulfur, carbon, oxygen, and you think that appropriate light element should be either one of these?
Well, it could be other combinations too. Silicon you not totally rule out, and this experiment particularly will just look at the silicon effect, but you could have another element, for example, hydrogen or carbon, if substantially low shear velocity, and you can still have some percentage of silicons. But what we're saying is silicon alone cannot explain the low shear velocities based on the measurement we have done. And this is important partly because there are quite a few papers showing silicon may be a dominant light elements in the core. That means the silicon, at least as far as we understand, as a half partition between solid and the liquid. So if silicon is a major element in the liquid outer core, then it likely also will become an important component in the inner core. That's why we start looking at the silicon effect.
And I have another question, quick question. So using the sintered diamond anvils, and you use a March anvil and you generated 30 GPa, 3000 Kelvin. And just I have a quick question. Which kind of heater did you use? Like a rhenium or lanthanum chromide or boron doped diamond heater?
This is a rhenium heater, but what I call a step heater. It's not a straight rhenium heater. The center part of the rhenium is a very small diameter. So in the center is you generate extremely high temperature, but you wouldn't be able to get those high temperature with a straight rhenium heater.
Okay, thank you. Now I get the meaning of the stepped heater. Okay, that's basically rhenium, and like a heating area is sort of the smaller. Okay.
Yes.
Yeah.
Well, we haven't published anything yet. It's everything I talked about is just in the process of publishing those results.
Dan?
Yes, can you hear me?
Yes.
Hi, Faith. Thank you
Hi.
for the nice talk. I have a question about your bridgemanite sample. Bridgemanite is really hard. I mean, I'm talking about strength. So when you synthesis takes a lot of effort. And then once you recover, if you need to shape it for a shockwave experiment, you need to cut and polish. Often we find that the water cooling is not desirable because it induces sort of like back transformation and all that. Can you share some aspects of those post-processing of the samples for preparing for the shock wave with us?
It's the sample is really hard, and the nice thing is it's very easy to polishing. So actually, you almost immediately know once you start polishing whether you made a bridge or not. And so those are relatively large bulk sample, and you are talking about back transformations. And for some of the long example, we're just using a water cooling and diamond cut, and with a relatively low speed. And I don't see any, because the sample is relatively large, so there is some capacity of the heat sink. I mean, it could be some amorphization on the surface, I don't know, but in general, those after polishing, we take a Raman, it's like a parallel surface.
Great, thank you.
Okay, does anyone else have a quick question before we sign off? Okay, doesn't look like it. Thank you again so much, Faye, for joining us today. Thank you for everyone for calling in. Appreciate it. And look out for announcements for our next seminar, which will be in September.
Okay, thank you. Goodbye,
Thank you.
everyone.